Hi folks, thanks for coming. It's nearly the end of the day, so I know you're here just for a little bit of light relief. In November last year, Google made a rather startling announcement. They had produced a quantum computer chip called Willow, and they claimed with this chip that they were able to do a computation in 5 minutes that would have taken not just the best digital computers, but the best theoretical digital computers, something like 10 septillion years. That's 1 billion times the age of the universe. Now, there was a bit of reporting about it, but mostly everybody went, oh, not interested. I think that's exciting. But nobody else was, because we've been here before. 5 years before, they made a similar announcement with a chip called Sycamore. Now, the point about Sycamore was that it did something much simpler. It did, in 200 seconds, a task that should have taken the best classical computers something like 10,000, 20,000 years. Now, IBM, who are also in this space, cavilled about this. They said, no, we could have done it in 4 years. But still, it was a really significant speed up. And this was appearing all over the press. It was appearing on the public press, and it was appearing in the scientific press as well. And everybody was asking the same question. More particularly, they wanted to know, what on earth is a quantum computer anyway? What exactly did they do? And why should I be interested in it? Well, spoiler, you should be interested. Because this stuff is coming. This is not science fiction. This is not like LLMs that are reaching their capacity. This is still pretty much unlimited, and we can see into the future, 5 or 10 years, where they will be incredibly powerful machines. What exactly did they do? Well, nothing useful. What they did was something like a benchmark. It's a thing called the random circuit simulation, but it's a thing which is designed to show the power of a quantum computer, which is precisely the place where a digital computer can't get to on its own. And we'll talk maybe a little bit more about what exactly that means. What exactly is a quantum computer anyway? Well, that's what we're going to spend the next 50 minutes talking about. Is this what you came here to talk about? Cool, I'm seeing some nods. Okay, before we can talk about what quantum computers are, we've got to talk a little bit about the nature of a classical computer and why we want to look forwards. Because actually, we have this sensation that classical computers are very, very good at their jobs. And if every year that goes by, we can see them achieving more and more powerful things. And yet, it seems that there are limits. Now, I want to do a quick recap. You probably know all of this stuff. But there are several types of problems that we want to solve on a classical computer. The simplest problems are trivial problems. These are the tasks that can be solved by a finite state machine with no memory. This is something which starts at the beginning and scans to the end. So this is things like counting the number of characters, counting the bits in a character, that kind of thing. There's a class of problems which is larger than that, which is the polynomial problems. These are problems which inherently need memory. But the character of these problems is that the bigger the problem you give to it, the longer it takes, sort of disproportionately. So, for example, a sort we can do in n log n. A multiplication table is n squared, that kind of thing. But the important property of these problems is that they're polynomial. They're pretty much bounded. There's a class of problems even bigger than that, which is the NP, the non-polynomial problems. Or, in fact, the non-deterministically polynomial problems. These are problems which, on a classical computer, on a parallel computer, where you can have as many threads as you want, then it's still polynomial. But when you're trying to squeeze it into one thread or a finite number of threads, then as the problem size gets bigger, then it gets exponentially slower. So these are not quite the intractable problem. So a task like this is factorizing. It's very difficult to take two numbers, to take a number and divide it into its 2 prime factors. But verifying it is dead easy. You just multiply them back together again. And multiplying them is one of these. So that's why we use prime numbers as the basis for cryptography. But there's a class of problems even bigger than this. These are the problems which are non-deterministically polynomially complete. These are problems where not only is it really hard to find the answer, it's really hard to know you've got the right answer when you get there. So these are problems like the traveling salesman problem. There are lots of very interesting problems like that we want to solve. We don't know how to solve them efficiently. Everybody's working really hard on it. Hang on, there's an even better picture coming up. Everybody's trying to work hard on it. But what we do is we don't solve those problems directly. Our best solutions are only ever approximations. But there's a class of problems even bigger than that. It's so big, we don't even have a name for it. And these are the problems which are so big that we can't even enumerate the cases. You see, in the travelling salesman problem, it'll take us a long time, but we can figure out every possible path through the cities. Here, you can't do this. And these are problems like protein folding, city traffic simulation, that kind of thing. They are continuous, they're not discrete, and they are very, very large, and they have this character to them that they're not even amenable to this understanding of what an algorithm is. And yet, a lot of the problems that we want to solve today are of that form. Now, we think, we don't know, and we'll talk a bit about this later on, but we think that quantum computers are going to be really good at a subset of these, but particularly there's an overlap here. So that is where the research is being pushed right now. Does that make sense? Is this unfamiliar to anybody? Okay, cool. Now, to give you an idea of the kind of problem that we want to solve, this is a picture of the chemical pathways for ferric sulfide. Ferric sulfide is a very interesting salt because it's involved in an awful lot of biological processes. We want to be able to model this. We want to be able to model this for gene modeling, for drugs modeling, things like that. Right now, we can understand the behavior of this part of this to within an order of magnitude. That's the best we can do. All of the rest of this, it's just guesswork and experimentation, crystallography mostly. So, it's clear that there is a need for a different kind of computing machinery. It started, really, at a conference for physics. Basically, as physicists were starting to learn more and more about quantum systems, they were trying to model these on classical computers and running up against this problem. I mean, none of the classical algorithms would work. The idea behind the conference was to see if there was any way to solve it. But one of the people who was there was Richard Feynman, whom I'm sure you've heard of. And he said, well, gentlemen, if what you're trying to do is simulate a quantum system, you probably want a quantum computer to do it. And like Feynman, it was one of those prophetic things that he even knew what a quantum computer was. But yeah, it sounds right, he was a smart bloke. So everybody started thinking about what that would even mean. So by 1985, David Deutsch, who was he was a computer science researcher, he took the mathematical model of the Turing machine and he modified it to try and express what a quantum computer would be. So he took our existing model of computation, and our existing model of classical computation, and rephrased it in quantum terms. Now the thing is, although the model is useful, we don't use it very much. We've got simpler models that we can use now, and I'll be showing you those later on. But we did at least have a theory of what quantum computation was. Then in 1994, Shor came up with this factorization algorithm. Now, this is the thing which got cryptographers really excited, because what this algorithm did is it said, if we're trying to factorize a large prime, to factorize a large composite, then that is an exponential problem. That's one of those really hard problems that I showed you. Shor proved that you could do it in n log n. Every time, you just needed enough bits. So that basically breaks all the cryptography that we're using today. And that was in 1994. Then, Grover's algorithm, now obviously searching is an important thing for computers to do. Grover's algorithm says this: if you have 4 cards on the table, ace, queen, king, queen, and jack, and they're all shuffled up, you have to pick the ace. Now, on average, it's going to take you 2.5 turns, 2.5 selections to find the ace, okay? In Grover's, you can do it in 1, every time, guaranteed. So this transforms search. Now, excuse me. Now, all of these were purely theoretical until 2001. It was built by a university, it wasn't built by a commercial company, but they built the first quantum computer. It was difficult, it was cold, it was very small and underpowered by today's standards, but it had 7 bits. And 7 bits was enough to run Shor's. It worked. It actually worked. And since then, that's just opened the floodgates. Because now, once you've seen one, there's dozens of ways to make other kinds of quantum computer. And the machine we're going to be using today is made by IBM, so I want to show you some pictures of it. I'm going to show you what a quantum computer actually is. Down here is a very tiny chip, which is, it's not silicon the way you'd expect it. It's not got transistors on it. It's basically got cavities and waveguides. This computer uses microwaves to do its work. But this has to be kept very, very cold, to within about 1/3 of a degree of absolute zero. So what you've got going on here is a number of things. You've got waveguides to conduct signals down onto the chip surface and to conduct the responses back off, and a lot of refrigeration. And these layers, they're separating the different refrigerants. Now, all of this is put into an assembly because, for various reasons, you want it off the floor because you don't want to vibrate it. But you can imagine a contraption like this needs an awful lot of automation to keep it running. So that's why I've shown this picture. You've got all this banks of equipment. There is... I thought I'd got... OK. It'll come up later on. They then wrap it up in a flask, and they pump it full of liquid helium, and they cool it down so that that chip at the bottom is at those ridiculously cold temperatures. And then they all stand around looking very pleased with themselves because that's what researchers do. If you want to know what's going on in all of that equipment and what's going on in there, there's a really good description there. You're going to get the slides, aren't you? OK, you got the pictures? Cool. So, how do you use a quantum computer? I'm going to use this as a symbol for quantum computation, and again, you'll see why in a moment. Fundamentally, that's that machine that you saw hanging from the ceiling. And this is surrounded by all of that equipment that you saw, which conditions the signals going in and out of it. But also, there is more conventional digital access on that. So what you then do is you sit at your keyboard, and using a normal computer, you talk to this bit, which talks to this bit, which talks to this bit, and then the responses come back. And you will find that actually quantum computers are now online as a service. There's a lot of them, and they're big, and they're pretty cheap to use. And this is fundamentally how they're set up. They are now a resource, just like any other resource that you're used to using. Now, the reason why they're interesting is because they're exploiting two particular quantum properties which we don't have in classical physics, and certainly we don't have in electronics. The first is, and you'll know some of this from high school physics, the first is the idea of superposition and collapse. If we take a light source and we pass that light source through a card, through a screen with two slits in, then what you end up over here is... I'm sure somebody was going to shout out. What you end up is a series of light and dark bands. And these light and dark bands are basically caused by the light coming from the bulb, shining through the holes, and interfering. Now, an experiment like this was known to Newton in the 1600s. But this is the proof that light is made of waves. And we've known about this for a very long time. What's interesting is that if you turn the light down, down and down and down, until you're seeing the individual photons, and when we did this, we found out that light was particles, they were individual photons. But when you turn it down to individual photons, what you find is that when they land, they always land in the bright bits. So you will see a flash here. And then the next one will land here, but they will never land here. And the explanation is that this photon, this one little particle, is passing through both holes simultaneously, interfering with itself as it passes through this space. And when it reaches here, what these bands are showing us is the probability of where the photon is going to land. And when you look at it, that's when it decides. That's the moment at which you see the flash. But right up until you look at it, this is all potentialities, and that's called the superposition. It could be in any of these states, but it's more likely to be in some states than in others. So the point is that this one photon, just one photon, if we can control it, we can control all of this. Now, you know this from school, right? Is this not familiar to anybody? Is this familiar to anybody, or are you just going, oh my God? Okay. Right. So what you've got is you've got the superposition going on here, you've got and the superposition is expressed as a wave function, and then you have the collapse of that wave function right at the end, which is how you get to see it. You know what Schrödinger's cat is, the cat that's alive and dead at the same time. This is what's going on. Here it's alive and dead, here it's alive or dead. Now the next principle that we need, now some quantum computers will operate just with superposition. D-Wave, I think, it just does nothing but superposition. But most of the computers that we want to really compute with use another principle, which is the idea of entanglement. Let's take our light source again that we did before. Generally speaking, things that generate photons generate matched pairs. Because what you're doing is you're converting energy in one form into energy in another form, and they're usually identical. So in this case, what we're doing is we're looking at the polarization of the photon that comes out. So these have the same polarization, these have the same polarization, and so on. Now, there's nothing special about that. That's just conservation of momentum. Okay? How do you measure the polarization? Well, what you have is you have a screen. And what the screen does is, well, depending on how you position the screen, if the polarization is vertical and the screen's vertical, then it lets it through. One whole photon. And if the screen is vertical and the horizontal is if the screen is vertical and the polarization is horizontal, it doesn't let the photon through, and you don't see a flash. And we know that if we set two screens along these two paths, then either we see a flash on both sides, or we see no flash. But what's interesting is that we never see a flash sideways. We only ever see a vertical flash or nothing. So this means that what's going on here, the polarizations here are random, but actually these polarizations are superposed. It could be any polarization. It's not until you actually look at it through the screen that it decides which it is. So that means every one of these is a superposition. And one way of thinking about this is that at the point at which you measure this one, this isn't exactly what happens, but it's a way of making it easy. This decides whether it's vertical or horizontal, and it sends that knowledge back in time to the source, which then sends this forward in time to that measurement. Not exactly, but something like that. But it does mean that you can have two objects completely separate in space and in time, but nevertheless whose states are intimately connected. This is what Einstein called spooky action at a distance, and this was the point at which he detached from quantum theory. Nevertheless, this is true, and this has been demonstrated time and time again, and I will show you this happening later on in the demonstration. Okay? And I know it's a lot to get your head around, but think of it as time travel. Make sense? Questions? Okay, because there's a test at the end, you know that. Okay, right, what's the next thing? So let's talk. Okay, I've just tilted the screen so you can see what's happened to these. So let's talk about how you build the quantum computer, what it looks like, what it competes with. In a classical computer, the way you work is with electrons. Fundamentally, you create charge. So if you want a zero state, if you want a transistor or a gate to be switched off, you place a bunch of electrons, a charge, in one location. And if you want to put the charge in another location, that flips the switch to be on. Now, in a quantum computer, you don't have anything like that. What you use is single particles. These have to be bosons. We'll talk about a bit more about what a boson is. But effectively, it has two states. One is the down state, and the other is the up state, where basically they spin. The property is called spin. Now, I've got some bosons here that we can have a play with. So this is a boson in the down state. Okay? It's not a real boson, obviously. You wouldn't see it from the back. And this is a boson from the up state. And what happens is, as you process with it, then you're flipping it between these two states. And we can measure what the state actually is. How do we measure what the state is? Well, we create, oh, I ought to explain this as well. So that's the down state, that's the up state, that state, and you can see why we're calling them rotations, that state could be up or it could be down. The moment it's in a superposition, okay? Just like you saw with the polarization, it has to be horizontal or vertical. This thing, when you measure it, has to be down or it has to be up. But we can rotate it into that state, in which case 50-50, it's going to measure up or down. In that case, 70% it's going to measure up, 30% it's going to measure down. But we've got these rotations going on, which we then collapse into one state or another. So here's our boson that we've made in some superposition. What we do is we create this strong magnetic field and we pass the boson through it. And as it goes through, it decides up or down. Its partner, which is still waiting for it, because remember, we generally make these things in pairs. The partner, at the moment at which that is measured, then decides what state it's in, and we can take that through other computations elsewhere and then measure those later on. So you've got this idea of upness and downness and this superposition in between. That's not the end of the story. Excuse me. So, here we've got our boson. Now, unfortunately, I'm sorry, I didn't make this stuff up. We have the down state at the top and the up state at the bottom. It's just how the maths works. This is quantum theory. Half of it is designed to be confusing. We can rotate it like that. We can rotate it like that. And the point about this is that those rotations also take part in the computation. They don't change its probability of measuring up or down, but what it does do is it changes the effect of other computations. We'll see some of those in a minute. So if you rotate it that way, and then rotate it that way again, then you can see it's still in its 70% state. Okay? So what we do is we represent this with a mathematical structure called the Bloch sphere, which is representing two things. It's representing magnitude on this axis, that's the probability that it's going to measure up or down, and phase, which was that property. And we need both of those numbers to be able to understand the state that the qubit's in. But that's not the end of the story. You see, the thing is that in order to fully represent the idea of rotations, and in order to fully represent the superpositions, we need a thing called the Lie field. Lie was a mathematician in the 1920s. He was a pure mathematician. He would be so offended that anybody has found a use for his theory. But the Lie field works like this. What we have is we have upness and downness on two different axes. So if we have a boson in this state, incidentally, now down is to the side and up is at the top. It's not my fault. So if we have something in the down state, like that, if we rotate it 90 degrees, did you notice? 90 degrees, it becomes up. But now, if we rotate it a further 90 degrees, it's now down again. But look, it's changed colour. We're now in a sort of an anti-down. So now, if we rotate it again, it's now in a sort of an anti-up. And we have to rotate it a full 720 degrees to get it back into the original state it was in. Okay, this is called the Lie field. I can show you another demonstration of this, which means that you will never forget it. I should hope. Now, you can all see the teapot. You can all see the picture on the front. This is probably easy to do left-handed. You can see the picture on the front. Now, if I'm going to rotate it 180 degrees, you can see the back of it, right? Now, I bring it back and you can see the front of it, and this teapot's behaving as you'd expect. But if I turn it another few degrees, now you can see the front, but you can see how I'm all twisted up around it. That represents the anti-down. And I go around another 360 degrees to get back to where we first thought of. So that is one complete Lie rotation. This is not a teapot, this is a Lie pot. See that it doesn't come off. Okay? But that's how the leaf field works. And to make matters even worse, each of these axes is complex. So although we're just looking at the plane, we actually have 4 degrees of freedom. Well, 3 degrees of freedom, because it comes out of the statistics and it comes out of the idea of rotation, that the sum of the squares of all of these have to be 1. Because whenever you're going to measure it, you're going to measure something. So that's the deal behind this leaf field. And what we're going to be doing, we're going to be computing by manipulating things through these various states, not just up and down, not just ones and zeros, but these complete phases. So what do we do in the quantum computer? In order to make a program, the first thing we do is we construct a program by initializing some qubits. Qubits are this unit of computation. They correspond to bits in the digital computer, although they're those phasey things. Now, the point is that this construction probably is going to involve some superpositions. It's almost certainly going to involve some entanglements, because that's what we're going to be computing with. What we then do is transform the problem to get from what we've got, from the statement that we've got, into something more like the solution that we want. And this is the program. And then finally, we take it to an end process, to a measurement process, where we collapse the whole transformation and get a result out. Just like those photons hitting the screen. But just like the photons hitting the screen, this doesn't give you the answer. It gives you a possible answer. And so you then do it over and over again. And gradually what will happen is you'll build up a picture of where the answers lie. One of Shaw's does, what Shaw's algorithm does, is it gets an idea of roughly where you'd expect the factors to be, and then it homes in on those and it looks closer at those. That's what the n log n is about, because you can get in very, very close in a series of steps. You don't do it all in one like we try to do on classical computers. How is that feeling now? Would you like to see a demo? Thank God for that, otherwise this would be a really short talk. Oh, come on. That's it. What we're looking at here is the control panel of that computer that you saw being assembled in the photographs. You can see several things going on here. Along here is what is called the staff. Qubits, bosons, are constructed at the beginning of the program and injected along here. And what we'll do is we'll place gates along here to transform the problem. And they go all the way along until they reach the end, at which point they get measured. Now, what we see here is an estimate of what the phase is going to be. And as soon as we start using this, you'll see those come to life. Over here is the result, the actual collapse. And since there's nothing in there right now, there isn't a collapse. But there's no way I can do this out the back of my head. Let's start like this. In fact, no, that's probably not the right one to use. Let's do an inverter first. OK, so what you're seeing here is that every one of these bits is reaching the end here in a down state. So it's each of them is guaranteed to read 0, and we can see here that the output state is 0, 0, 0. If we put in, here we go, this is a gate called a NOT. This does nothing more complex than that, or similarly, that. So you can see the effect of this over here. You can see it's filled up with blue. That says it's certain to read up. And over here, you can see that out of our 1,000 runs, all of them have shown 0, 0, 1. Now, it will be no surprise if I put another one in. It takes it right back to where it first came from. And each time I'm doing this is a simulation right now, but each time I'm doing this, it's running 1,000 simulations of that program to produce that result. So what I'm going to do now is I'm going to delete these two, and I'm going to put in a different kind of gate. This is a Hadamard gate. And what this does is it rotates it 90 degrees, or 180 degrees, no, 45 degrees in the leaf field. So it goes from there to there. And we can see the effect of that. Over here, it's 50-50 full. So that says 50-50 going to be up or down. And we can see that here. The last digit is 50-50 up or down. Now, this is not challenging, is it? This is pretty straightforward stuff. I'm going to show you another function. This is called the conditional knot, or snot to its friends. It's not my fault. Now, what this does is it inverts this line if the control line is up, but not if not. So right now, the control line is down, so the result of the controlled line is still down. But if we put an inversion, anybody care? Switch them both. So this is sort of an exclusive OR. Now that's pretty cool. But it's not really useful. What happens if we replace that with a Hadamard? Well, several things happen. First of all, what the Hadamard does, remember, is it puts it into that superposition. So we can see the superposition in Q0. And remember what the snot does. The snot says, if it measures up, it flips it. If it measures down, it doesn't flip it. Which means Q1 must also be in a superposition. Because it's it measures up or down depending on what that one's measured. But do you notice how the ring has got smaller? What that's doing is it's saying these two states are impure. It's saying that actually these states don't belong to either qubit on their own. They actually belong to both. It's kind of a dilution. And we can see that down here. That either both of them switch at once, either both of them switch at once, or they don't switch. This is exactly the entanglement that you saw with the photons a little while ago. This is called a Bell state. I'm sorry, let me move the cursor so you can see it. There we go. This is called a Bell state, and you're going to see that this is incredibly useful. There are other things that we can do. There are lots of different kinds of gates we can play with. Let me get... Here we go, let's try this one. This is a Z transform. I don't know why that hasn't moved. Actually, I do know why that hasn't moved. Here we go. So what that Z transform has done, the Hadamard has gone from here to here, and then the Z transform has transformed there. And we can do progressive rotations there as well. There are a whole bunch of these transformations. And these are all about changing phase. And they all become part of the computation. Now, I could spend hours playing with this. You could spend hours watching me, I'm sure, but we've got a limited amount of time. We've only got 15 minutes left. So unless there's something that you specifically want to see, I'd like to move on. I'm here for the rest of today, and I'm here tomorrow, and I'm happy to get the computer out and play with it some more. So are you happy for me to move on? Okay, cool. So, in the light of what you've just seen, is this explanation making more sense? Okay, cool. That was your demo. Now, this is the picture from 5 years ago. People were very, very excited by that 7-bit computer. But this computer, the Sycamore, people were really excited. This really hit the mainstream. And so suddenly people started pouring money in it, throwing research into it. It stopped being merely an academic toy and started to become something much more powerful and much more interesting. Here we go. Over the next 5 years or so, there was loads and loads of announcements coming from all over the place. You'll see that most of these are coming from the scientific press. They were trying to do a lot of different things. They were trying to build bigger computers. There were more players coming into the market, not just IBM and Google, but Amazon was in the market. They now have a service offering. Honeywell, why were they interested? But turns out, yeah. They're trying to get more stable bits. There's a property of a quantum computer called its quantum volume, which is roughly the number of bits it's got multiplied by the length of time you can keep those bits coherent before the noise takes over. And so that is a good representation of its compute power. So there have been lots of moves in order to get the quantum volume up. And obviously, lots and lots of work being done on applications. So cryptographers have been getting very excited by it. Algorithmicians have been getting very excited about it. Simulations and, whisper it quietly, AI, because this is obviously a natural fit for AI applications. I want to put this into a picture for you. What you see here is a number of major announcements. Again, since the start, this was that original 7-bit computer that I mentioned at the beginning. And then these are a series of announcements over the years. This one, that one was Sycamore, and that one was Willow. Now, these red ones, you can see they're a bit of an outlier. That's the D-Wave computer. That's an annealer, not quite the same thing as what everybody else is doing. But if I superimpose a trend line over these, then you will see that they're following more or less straight line trends. And I want you also to notice that it's a logarithmic scale. What is happening is that these quantum computers are doubling their volume every 18 months. Does that sound familiar? Now Moore's law is over and it's not happening. It's happening in GPUs and it's happening here. And unlike in GPUs where it's been precipitous, here, it's been steady work over a long period of time. So I have a question for you. If you could go back in time to the 1950s, taking with you everything you know about digital computers, what would you do with that knowledge? Well, that's where we are. Quantum computers are at the state at which digital computers are in the 1950s. And there is no theoretical limit that we know of how far that can go. Moore's law ran into theoretical physical limits. We are not even close to it with quantum computers. Now, somebody is going to have to program these things. Who but numerate programmers? So, I actually am not selling anything here. I'm giving this talk because I love this stuff, and because it's a tremendous amount of fun, and because when I'm 80, I'm going to have a job for life, which might not be very long when I'm 80, but you get the idea, right? Okay, so let's talk a little about the kind of research that's going on, what's going on behind that graph. First thing is that there's a massive amount of engineering. We're trying to build bigger scales. Obviously, that's a big driver. And we'll talk about what Willow did. Willow was the Sycamore chip was 53 bits. Willow was 110. It was only twice the size, and yet it had that tremendously higher performance than the Sycamore chip. We're trying to get high temperatures. At the moment, they all operate superconducting for very good reasons. And we'll probably never have a machine that doesn't rely on superconducting. But if we can get superconductivity at 70 Kelvin, that's something we can embed in a computer, in a laptop. And that means we will have a quantum processor alongside the TPS chip. And that is not far away. It might be 5 years, it might be 10, but 70 Kelvin superconducticity we know is theoretically possible. Error correction. I mentioned about quantum volume. You've got to build this state. They say it's a delicate state. It bloody well isn't delicate. It's tough as old boots. These things are what prop up space and time, so they're not that delicate. But you do have to be able to protect them from interference. And so people are working very hard on how to keep these states not just clean, but to correct them when errors creep in. And you'll see that that was one of the things that made Willow so successful. What sort of applications are we looking at? I don't know why they didn't go. We're looking at physical modelling. I showed you that chemistry. We want to understand weather better. Weather uses enormous computer power, and it still gets it wrong most of the time, particularly in Britain. But if we understood more about how these systems work, and particularly the catastrophic systems, the butterfly effect, those are things which quantum computers can handle very well. So, for example, if you're doing city planning, one of the problems with city planning is that it's not the bulk behaviour which is important, it's the individual accidents or individual slowdowns or somebody parking on the yellow lines, and that can gum up a city across 2 miles. And our present systems are not very good at modelling that, but quantum computers would just home straight in on those special cases. We care very much about optimisation. We were talking about a travelling salesman earlier. Half the world runs on optimisation algorithms. It just wouldn't function without them. And yet, they're clunky, they don't work very well. At best, they only give us approximations to the answers. So there's a lot of interest in quantum computer optimisation, which is going to be immediately transposable into other fields. Finance. High finance is just a closed book to me, but I know that they've got some very clever mathematicians, and they're very interested in this, not just for doing the computations, but for doing the very high-speed computations, and doing those sort of computations that you don't quite know when they happen. They're also very interested because they want secure communications. And it's obviously a fit for AI, because AI needs a lot of training, it needs a lot of data, you need to look at lots of different cases, particularly when you're training a model. With this, you can superpose 1 trillion runs all on top of each other in one single run. That's the point of the superpositions, that you're actually not dealing with one statement of a problem, not one data set, you're dealing with an infinitude of data sets, but they're synchronized together. And then finally, security. Security is very interesting. They're trying very hard to crack current encryption. We do know that we have algorithms that as soon as the computers get big enough, will literally open every encrypted message in the world. And we also know that intelligence services the world over are slurping up encrypted messages from everybody in the hope that one day they will be able to open them. So it's not enough to delete your browsing history, sorry. On the other hand, there has been efforts to design security and encryption algorithms that will stand up to a quantum attack. And there was actually an effort by NIST. It was a competition to produce a new standard. They had about 15 contenders at the beginning. About 2 years ago, we thought we had a good solution called Rainbow, and they found that it was absolutely quantum secure. Unfortunately, they cracked it in 2 weeks on a digital computer, so that was a bust. There's now an algorithm which we pretty much think is going to be adopted, but there's a slight problem because up until last year, basically this was a worldwide effort. All of the world's security services, including the unfriendly ones, were participating in this. But early this year, the Chinese security services said, we don't trust the Americans not to put a backdoor in. So they said, we're going to go our own way. And so they disconnected from the effort, and they're developing their own algorithms. If you really want security, probably you want to encrypt with one and decrypt with the other. Or double encrypt with both of them, because each of them is designed to be safe against the other. So it's still a developing field, it's still a complex field, and it's still a very politically fraught field. But it gives us something else. All right, that's basically what I was talking about. Yes, it gives us something else, and there is such a thing as quantum communication. I didn't show it to you. Part of what I've got in the demo is something called quantum teleportation, where you take a state and you place it somewhere else physically, with no possibility of anybody in the middle of ever seeing it. And if they do try and look at it, it destroys the state, so you know you've been tapped. We already know that the Chinese are sending quantum encrypted messages through satellites around the world between their embassies. And I think it was about 3 years ago, they built a quantum network, quantum secure network, in the New York subway based entirely on photons, using the fibers that were already in place. So we know that quantum communication over very long distances is here now and is practical. Which brings us up to today. This is Willow. You can see how much more, how much bigger, how much messier it is than the Sycamore chip. But in spite of that incredible improvement in performance, what they did was not that great. I mean, first of all, it was a bigger chip, but we know how to build bigger chips. It was only 110 bits. But they did something else. They built error correction in. And everybody thought that as you build bigger error correction, basically as you replicate the bits into more and more cells, that you'd lose the capacity. But what Willow did was it said you can actually have this sort of overlapping error correction. So in fact, it raised the capacity and it raised the coherence time. It basically gave you a double payback on the quantum volume. Okay. Now here, I want to try and show you a picture of the problem space that we're interested in right now. Here, on the vertical axis, are problems which are more or less difficult. The higher up it goes, the more complicated it is to solve, the more suitable for a quantum computer. From left to right, we've got usefulness. So we have already had photonic systems running. That's what I was talking about before. We've already had time crystals running. I think they cracked that about 6 months ago. D-Wave thinks they've cracked icing. That's a chemical problem. But like everything D-Wave says, nobody really believes them. But over here, we've got chemical simulations. Over here, we've got machine learning from a quantum basis. These are things that we can just about do with modern computers, but they're creaky. And again, with modern computers, we're up against the limits of what the physics will allow us to do. As we go up here, we start to become more interested in real quantum effects. And this, the random circuit sampling, is what both Sycamore and Willow has done. This is pretty much the standard benchmark for quantum computing because we can't even think of anything harder to do than that. And it is truly a fiendish problem. Okay, I love this space. I think this is really interesting, and what I've tried to explain to you here is that, or what I've tried to demonstrate to you here, is that you don't need to grapple with all of the hard and spiky bits of quantum theory. This has been reduced, this has been simplified. We've got this concept of gates. So in the same way that using a computer now, you don't need to think about individual bits. You certainly don't need to think about the electronics. That's all been done for you. We are working with the same kind of abstraction, and you can think into it. So I encourage you to come and get involved. The water's lovely. These are some absolutely superb books. Nielsen and Chang is the absolute classic text. It's quite a big book, but it takes you from the very beginning up to the very end. It tells you enough quantum theory to understand it. It shows you the basics of the maths, talks about the engineering, talks about algorithms. It is an absolutely smashing book. This one might be worth a go. It's called Quantum Computing, A Gentle Introduction. They lie about that. And if you really want to understand the underlying quantum theory, which once you've gotten into that, I suspect you probably will, this is quantum field theory in a nutshell, which is truly a nutshell. It's truly a good book. It's truly a bloody big nutshell. The computer that you've just been seeing, you can get at IBM. But there are other players in town. Google is very interested in getting you involved in theirs. Amazon is very interested in getting you involved in theirs. You don't have to finger paint like I was doing. You can actually program these things in Python. There's a terrific article on Wikipedia about this. It's, if you don't want to go and buy these, this will get you started. The theory, it's one of the strongest articles, I think, on Wikipedia. If you want to know what they did with Willow, this is kind of a brag screen. They're very, very keen on this. But there's a lot of background in here. It's not just about Willow, it's about why Willow was important and technologically how they did it. And of course, talk to me. Because I really love this stuff and I love talking about it, as you can see. Okay, I have 10 seconds left. Has anybody got a very small question? There is a joke that they will break RSA 2048. Sorry, not a joke, there's a bet in place that they'll break RSA 2048 by 2048. I think it's a $1,000 bet. That's 50-50. But it's not too far away. Anything else I can tell you right now? Well, in that case, I'm out of time. I'm going to be frogmarched off the stage. Thank you very much for your time.